Welcome back. I guess I do the afternoon sessions now. We have only 2 sessions left. I have survived the wintry mountains behind Tehran to the north. We had a very good time with the students yesterday. So I hope I still have some good energy. Let's see. Oh, and one of the students, a few students asked me what this means. I do this a lot. That means in quotes. So this is a robot, something like that. That means, I'm not calling it that, but it's often quoted as that. That's what I mean. So it's an American gesture. It's very common. So now you know. We were in the middle of filters. I'm just about to finish filtering, which is good because I have quite a few more parts to cover before the class is done. This was the last thing we did, which was shadow information spaces. This was a generalization of pursuit evasion types of problems. We want to count the number of bodies outside of the field of view in these shadow areas, right? Remember that? So there's the shadow region, which comes in components. This is very fast review because it was 2 days ago. Most people forget what they did 2 days ago, right? So we do this. We have the 4 cases that are very common in pursuit evasion. You have appear or disappear going up or down here. The shadow, the brown area, appears or disappears. You have split or merge. And then I talked about what information do we have. We add a shadow, we remove a shadow or add a shadow for disappear and appear. We have a split relation and a merge relation between 3 shadows whenever they split or merge, right? So we can imagine there's this flow of shadow events as we go. And as somebody asked at the end last time, there are also what we call field of view events, but I'm ignoring those today, but we cover that. So if something comes into the field of view, we have an event for the filter that we're making for that too. I'm mainly keeping track of these, but we should pay attention in general to the field of view events because in pursuit evasion, the game is done if the evader enters the field of view. But for this problem, it's more general. So we can say, maybe it continues. Maybe we have to find more evaders. I talked about the pursuit evasion filter where you just have a label of 0 or 1. And then we have these rules of updating, which go all the way back to our original papers on pursuit evasion. Yes?
Which one appears separately?
I'm making a general position assumption so that the appearance is the appearance of a single shadow. So it appears with a 0 label, and split and merge. Split just copies the label, and merge is like logical OR. Right? This is where we ended last time, and I think I updated this. There was an error right here, so that was the thing to fix. This is a very simple way to make update rules if we're trying to keep track of the bounds on the count. So you have lower and upper bounds on how many evaders, if you like, or whatever they are, moving around, their bodies in general. So if I have appearance, I'll assume there's nobody there. This is very simple. I just, in the case of splitting, I just propagate in the case of splitting, I just propagate the lower bounds, and I copy the upper bounds. Oh, sorry, no, I copied the upper bounds here, right, from the original S that split, because all of them could have gone to one or the other, right? And then for the case of lower bounds, either one of them could be empty. So that's a very simple way to do that. And for merging, I just add the individual lower bounds, and I add the individual upper bounds. That gives you kind of a weak sort of filter, but it's not completely telling the whole story. There's a little bit more here, which is quite interesting. So let's C, C prime, and C double prime be the number of bodies in each of the shadow components. If there's a split, then we have this algebraic relation, right? Isn't that true? If there's a split, then the gap that got split, the total number of bodies there must be equal to the sum of the number of bodies in the 2 shadow components that it split into, correct? So it's very interesting. So you accumulate an equation. In the case of merge, you accumulate an equation. The 2 individual shadows that merge are going to be equal to, in terms of the number of bodies, to the number in the shadow that they merge to. So here's what's interesting. The information state in this filter is actually a polytope. Right? So a high-dimensional polygon, a polytope. Convex polytope, it turns out. Because here's the interesting thing. So I have all of these shadow components. Each one could have some number of bodies, right? So let's suppose there's a variable for each one of the shadow components. Say the variable is some xi. I don't have it written here, but some variable. And it has to be an integer because the number of bodies is an integer. And then I could say, all right, consider the integer lattice now. So if there's m shadow components, then consider z to the m. Z is just the set of all integers. I guess there cannot be a negative number of bodies, so maybe that could be the natural numbers union 0 to the m if you want. That was just being kind of compact. And then what happens is we gather all of these constraints here. Right? So we have lower and upper bounds for each of the shadow components. Those are constraints on this lattice. It's a grid, right? Lattice or grid. And then all of these equations here, which are very simple equations, further constrain the lattice. So there's a high-dimensional polytope that is the information state. And then if you want to figure out how many bodies there are in a particular shadow region, you end up solving what's called a simple integer linear program. Now, integer linear programming is NP hard, you may know in general, but it turns out this particular program is very straightforward because it only has these kinds of constraints. And you can solve it very efficiently using max flow algorithms, it turns out. So to answer any question about what's the upper and lower bound in a particular shadow, taking into account all of these constraints. So it's very interesting. So it's a filter where you get a polytope in every stage. And you keep updating the polytope because you get new constraints here. And if you want to have, that's just for like one color, let's say, upper and lower bounds on counting the number of one color. If you have multiple colors, it turns out you just keep a vector of bounds and it works in the same way. So it's not really very hard. One thing that's really interesting about this problem, suppose I want to do the following. Here's how it's related to pursuit evasion, right? So suppose I have distinguishable bodies. Suppose every body is a different color. And I want to come up with a strategy to count all of them in the environment, but they can move. What's the right strategy to do that? Right? If I want to count, say everybody here is trapped in this building, right? But all of you are nicely distinguishable, right? And let's suppose I want to count all of you. What's the right strategy for doing that? Any ideas? It's the same solution, I want to say, as the solution to the pursuit evasion problem. Because what you want to make sure is that you see everyone at least once. And that's how you would search and count them. So counting and pursuit evasion are very closely related. So I suggest to you, if you're interested in pursuit evasion problems, which I know many of you are, to really think about this general class of upper and lower numbers on the number of bodies here, and try to figure out under what conditions can you manipulate the count, right? Different levels of distinguishability and so forth. Can I force it so that one of the rooms is empty? If I make an assumption like the people do not want to be seen, which is what happens for evaders. And so then there are no field of view effects, nobody enters in here, and then I think about how to force the numbers in some interesting way. Then you can go back and take all of the pursuit evasion papers and generalize them to these kinds of information states and ask interesting questions. So I can keep the whole room busy with pursuit evasion extensions that involve this if you're interested. All right, and we can put mirrors in too. Okay. Here's one more, and so this will finish this part, is gap navigation trees. I already talked about the gap sensor. Remember that one? Very nice sensor. It just goes around and tells you where the gaps are. And here's how they may look at a given stage K. And then there's an information space that's going to be a space of trees. I wrote I trees here. And here are the same 4 events. And I'm going to do surgery, let's say, surgical operations on a tree. And the leaves of the tree are going to correspond to the gaps. And if you're in a simple polygon, then the gaps also correspond to the shadows, just like a shadow information space. If you're not in a simple polygon, then 2 gaps might bound the same shadow, because you're looking behind a hole. Well, you cannot look behind the hole, but there's a hole behind it. And so if we disappear, it's going to correspond to deleting a leaf. If we appear, we add a new leaf from the root. If we split, we delete a child of the root and then raise its children up. And then if we merge, we're going to insert a new child and lower the children. I will show you how this works. This is how the filter works. It's a filter over a space of trees. Here's the appear and disappear. Again, these are familiar from pursuit evasion and other things. I showed this for shadow information spaces. I just drew a curved environment because this is the way an inflection looks. Very pretty in the curved case. So we move up and down. And we have split and merge, same kind of thing. Pay attention to the gaps though. So if I draw this as a gap, I mean that little part sticking out there is a gap. It's just combinatorially represented, like gaps, just points around S1. In fact, their precise location doesn't even matter, but you can imagine they have an angle that's precise, but it doesn't even matter. So that gap is there because of the inflection, right? And then when I move up, it disappears. So the disappearance and appearance of gaps is the same as the disappearance and appearance of shadows. Splitting and merging of gaps, same thing, right? There's two gaps up there, and it goes into one. So all the same idea, all these things grew out of our original ideas on pursuit evasion, so that's why it looks like that. I keep thinking in the same way, combinatorially, but going in maybe an unusual direction compared to what people might normally do in computational geometry, because I'm trying to go in a direction that I think is motivated heavily by robotics and what the kind of concerns are. So here's the idea. So if I go back and make this filter here, and I do these operations, I should have a, let's see, well here's where it shows the operations. So let's suppose I have a tree here, and every leaf corresponds to a gap. All right, that's the tree. That's my filter information state here. Then, if I move a little bit, I get the appearance of a gap. I just add it to the roots. Now I have 3 nodes. Here's another one. Sorry, this is a little small. I didn't have time to put out a big picture of it. Over here is a merge. So what happens in a merge is the 2 gaps up there that merge into one. So we take these 2 gaps, we push them down, and we put an intermediate node here that says this is a merged gap. It was formed from these guys. So all you're remembering is whenever merges are done, you're remembering what were the gaps that got merged. Just remembering their labels, let's say. And I continue to do this. Let's have, when it's disappearance, I just delete it. That's easy. When I have a split, if this gap is going to split, I take its children and I move them up to the root. So that's all the simple operation is. When I do this, it turns out I get a tree that looks like this. And I took the tree, I mean, this is how the tree really looks to the robot. It's just a combinatorial tree. But if you embed that tree in the environment, it looks like this. Here's where the robot is, and here's how the tree is. It's learning something exactly called the shortest path graph, or visibility graph, but the reduced one for shortest path motions. These are called shortest path trees in the literature. It's a subgraph of the shortest path graph. It basically tells you how to get everywhere in that environment optimally from this location right here. Do you believe that? So how do you use it? The way to use it is, if you want to go somewhere like, let's say here, all right, maybe there's something you saw here and you want to get back to it, you do an operation called chasing. You chase this gap here, and then that you saw it here. It turns out that's called gap number 2. It's going to be the parent here. You chase that one there. So you chase that. When you get here, you see it splits. 2 corresponds to this pocket. You chase the child here. I want to go to 3. So I chase the child this way, then I move this way, and then all of a sudden 3 disappears, and then I can see right here and go straight to something if I have a visibility sensor. So even though the robot cannot measure distances, this is really strange that happens for this now. The robot cannot measure distances. It only measures gaps, and then it executes motions in terms of the gaps, but it can do distance optimal navigation. Isn't that weird? So it can do distance optimal navigation without sensing any distances. Is that counterintuitive? I hope so. That's very strange to be able to do that. So that's the idea for these gap navigation trees. We proved that this structure gets learned by exactly these trees. So as far as the robot's concerned, this environment here, these 5 environments, all look like this. Because for the task of optimal navigation, all it needs is this. So it doesn't care about the exact geometric maps. This is enough, because these all have the same shortest path graph, which is a very nice way of combinatorially thinking, right? So that's the idea for that. I have a video, but I'm not sure if it's, let's see. This one probably won't play it. I'll get it. No. So if you were, let me try. Let me see if I can play that. It's going to go kind of too fast, but that's how it looks when it explores, and it makes this kind of graph. And then when it's done, it will have the shortest path tree that it can use to get back to any place where it's been before by just chasing the gaps in this tree and forcing them to split. So that corresponds to traversing the shortest path graph. Sorry, that was kind of way too fast. Maybe one more time. So it starts off with only the gaps that it sees, and then it keeps merging and merging and merging until it learns the whole structure. There's a very simple procedure for learning. You just keep chasing gaps that you have not determined whether or not they are splittable. If they are splittable, then you chase them, and then you keep doing that, and that's the learning procedure. And then when you're done, you can do the strange thing of distance optimal navigation without measuring distances. All right. Any questions? Yeah.
Environment is known or unknown?
No, completely unknown. That's the point. It's an unknown environment. It's only assumed to be simply connected and piecewise analytic. So it could be polygonal or not, but unknown environment. There's no holes in the middle of it, because then you go around and around. We have a version of the algorithm for going around, and you need a little bit more sensing information for that. So this should be amazing, right? Unknown environment, no localization. You cannot measure any distances. You cannot measure any angles. All you get are the gaps and the ability to chase a gap. And I gave you how to do distance optimal navigation among all possible Euclidean paths. So I think that's pretty strange, right? Yes?
The last section, you say that gap sensors does not exist in physical environment. You need a laser scanner.
No, I did not say that.
How you can find this gap in this environment?
Well, maybe I can find it because I can use vision to notice where there's a doorway, and maybe I know there's a gap there because of that. So vision would be an example of without a laser scanner, you know there's a gap. So I'm just saying the virtual sensor is a gap sensor, however you want to implement it. If you have a laser scanner, I'm still telling you that the information you need in the filter is much smaller than what the sensor produces. So I'm saying that you can pre-process your gap sensor to determine the gaps, and then from that stage forward, all of the robot navigation does not worry about localization or anything. So any errors you get in measurements and stuff, as long as you can detect the gaps, which may be hard, may be easy, depending on the sensor, everything else just uses very small information. That's kind of the point. So even, it's important to understand that the navigation strategy is still very simple. Yeah, that's good questions. Anyone else? So that finishes part 3 of the slides, which is, remember there were spatial filters, which had triangulation, and temporal filters. And we had a generalized triangulation principle, generalizing ancient forms of triangulation by just intersecting preimages. We took the preimages of observation histories and went from that to the state trajectory space. We looked at temporal filters. These can be viewed as traveling through or walking through an information space. Right? If you're always producing some kind of information state, I showed you one very simple one that only had 4 information states for keeping track of whether 2 bodies are in the same region. Remember that? So, the shadow information space is another one. It's a polytope every time. So the gap navigation trees has one where it's a tree every time. So very different kinds of combinatorial objects, let's say, could be elements of the information space, depending on the problem. Start with the task and find what the structure should be for your problem, right? Whatever the minimal necessary. We looked at non-deterministic, probabilistic, and combinatorial filters. Combinatorial being a special case of non-deterministic when you have combinatorial types of models. And I showed you 3 different examples: obstacles and beams, shadow information spaces, and gap navigation trees. So that's the idea. You define these virtual sensors and study the preimages carefully and try to make reduced complexity filters. Questions about this part? Yes?
You talk many people in this section. Can you describe what the power of these features, each of them is powerful than other features?
Yeah, that's very good. So if I go back to my comparing the power of sensors, well, which is in the previous set of slides, let me just describe it here. So remember when I made this diagram like this, we have H2, let me draw it let me go through it, sorry. X goes to Y2, and that's with H2, and we go to over here to with H1, we go to Y1, and then we wanted to know when does there exist G, right? So when I made that diagram, if it turns out that there exists G, and if it turns out that you can compute G efficiently, right, then you can take sensor H2 and replace it with H1. H1 is more powerful than H2. So in any of these filters that I've given, Let's be careful on the probabilistic ones, but let's say the standard, the filters I've been defining, these combinatorial filters, non-deterministic ones, you can simulate H2 using H1. So if that's the case, then the entire filter will work with the more powerful sensor, which then causes me to want to go in the opposite direction and say, what is the weakest sensor that I can still use until the method fails? And that's where I'm interested in being, in terms of virtual sensors. In terms of the physical sensors, then you got to figure out what to do in the physical world to get that critical information that you need. That's the idea. Thank you. Anyone else? All right, I'm going to go to the next part. Let's see, I've done 3 parts and I have 3 to go. Do you think I'm going to finish? Probably not. But the 2 of the parts are very short, it turns out. This part's kind of short coming up, and the very final part just has some conclusions and such. So it won't take up too long. So slide 4. Let's see. So I want to talk about planning with perfect sensing. And in some way, I can consider what we've done so far. I started with sensing and then made filters, right? But the world of planning has started with planning and then considered sensors as an afterthought. Like, oh no, now I need all of this information. I better get some good sensors. Right? And so what I'm trying to do here is I'm going to give an overview of how people think traditionally in planning, how I thought for many years and many other people, and I want to give an overview of that and some of the things I've done in that context. But I also want to have us feel guilty about it too. Like the information requirements are too large, the models are too perfect, so that we can then go back and do planning in the next part. The part after this, part 5, will be planning with imperfect sensing, with a lot of ambiguity, because that's where I really want to be for this course. But I still want to show you what the progress is for this. And in some sense, this could have come before, at the very beginning of this course, but I thought it fits here. I wanted to give you the sensors and filters first, so that we can appreciate how powerful the sensors are for these models. So that's the idea. So maybe I suppose I have X goes to Y, that's my bijective sensor, right? Let's take the top sensor from the sensor lattice, the most ridiculously powerful thing we can imagine. We'll just make everything perfect. Maybe it's E cross S1, as we said before. Maybe it's some subset of R2 cross S1 across a bunch of environments, maybe an uncountably infinite collection of them, right? And more generally, I may have, instead of R2 cross S1, I could have any configuration space in here. So the information spaces I talked about, which all look very pretty, I think, just become X, the state space. Because you're going to make a filter that's so powerful that you just get to live in the state space all the time. I think that's called state estimation, right? Right? You make filters that estimate the state all the time. So that's what we're going to assume. All of the beautiful structure is destroyed then, I think. I feel like, of the things we talked about. You're at the top of the sensor lattice all the time. No uncertainty with respect to sensing. So once this H is given, sensing is trivialized, right? So let's continue with trivialized sensing. Right? Trivialized, and sensing is not interesting. It's so powerful that it's not interesting. Well, if you go back historically, I like to look at this. I looked at some old pictures at some point. This is Nils Nilsson there, leaning over the old shaky robot from the late 1960s at Stanford. You've heard of Nilsson, maybe? A lot of people. Very nice guy. I had a chance to meet him when I was a postdoc at Stanford. Very nice, very smart guy. So at that time, they developed planning. They thought of it as automated sequential decision making. And it had a very heavy emphasis on algorithms and computation and logic, especially at the time, because, well, they're computer scientists. And what I found amazing, this old picture was there too, where they put some obstacles in the lab and they had this robot moving around, and very clear that people were already thinking about sensing and mapping and planning and collision avoidance and all of that stuff in the 60s. I find quite amazing. So the issues are still there. The only difference is we can remove that cable on top now. Right? So they had a lot of things to power them. Well, now we put cables on top of humanoid robots and a lot of that. Okay. So what happened throughout the history was, the world is, let's say, continuous. If you talk to people in physics, they'll tell you that's wrong, but we can imagine that we grew up in Newtonian times or something like that, and it looks continuous. That's what calculus is supposed to make us believe, right? But computation is set up to be discrete. That seems to mean to me that if you're going to do algorithms, especially planning algorithms, you're going to need discretizations, right? Of some kind. Discretizations do not have to lose information. They can be quite perfect and exact. Computational geometers know that, right? That's their surprising contribution to the world, right? That you can discretize continuous problems and lose no information. It's quite nice, right? So anyway, back in the day, people in the 70s did a lot of logic-based representations, things like strips, planning. Maybe that goes back even to the 60s, but got popular across the 70s. They reason about grids. Then there was combinatorial motion planning, which I would say took quite an infusion from computational geometry. Yeah, in fact, if I'm not mistaken, you know the original book by Preparata and Schimmels. Tomás Lozano-Perez told me a few months ago that he was working at in an industry lab where he was able to get a copy of Schimmels' work very, very early on. He saw it come off the printer and he was looking at it, and it had this unusual way of thinking, and I think that inspired him to do this nice algorithm I will talk about in a bit, where he was thinking combinatorially. So I was amazed that he was thinking about this in the late 70s, but it was from some kind of coincidental contact with computational geometry. So very early on, there was this contact, and then in the 80s it really boomed, in the early 80s especially. Then came sampling-based planning to be practical, and I will explain that in a bit. The thing to understand about planning is that the problems are implicitly encoded in the sense that you do get input for the algorithm. The input will tell you maybe a model of the table, where the walls are, how the geometry of the robot is, but it will not tell you how the configuration space looks. If you want to know where the obstacles are in the high-dimensional configuration space, as hopefully you saw in the earlier part of the tutorial before I came, it's complicated. It has very high complexity. It's very hard to represent these things. So you're often dealing with a much bigger problem than what's been presented as the input. Otherwise, it could look like a simple graph search. You know, we all know how to search a graph. Big deal, right? Here, it's like as if they gave you a way to describe an enormous graph. And you have to just determine how much of it you want to construct in order to solve the problem. And so if I just give you the big graph, then you just search it. Use a breadth first search and you're done. Who cares? All right. So I say all of that, and that's right. So the problem is, even with perfect sensing, complete models, everybody's happy. The space in which you're searching is much larger than the input that you've been given. So you can construct lots of that. Even going back to the old logic-based representations, they give you some rules. You know, like if I have some preconditions. Do you know strips planning? You might have seen that in basic AI courses. You know, if I have some preconditions, I apply some logical rules or operations. Operators, I believe they're called, and they will change conditions in the world. They will make certain predicates true or false, so you can keep applying it, and you're discovering essentially a kind of state transition graph during execution. You still have the configuration space, which is the set of all transformations you can apply to the robot, all geometric transformations. Usually we like to consider it as a topological manifold. People in control theory tend to like differentiable manifolds, but that's because control systems are expressed with differential equations. The path planning problem is not expressed with differential equations in the basic form, so we can just use what's called a topological manifold. It's less known among engineering people, but it turns out it's much simpler. So when you study it, it's very nice. I'm not going to do that kind of thing here. It usually just looks like, let's say, some m-dimensional surface embedded in Rn, and m is what we call the number of degrees of freedom of the robot. That's the dimension of this configuration space. Some cute examples. Here's another picture of that autonomous vacuum cleaner, maybe a better one than what I showed before. No, I showed this one before, actually. Autonomous vacuum cleaner that has SE2, or R2 process 1, before we remove the obstacle. Maybe we have a autonomous unmanned aerial vehicle, right? You guys know about those in Iran, right? So, that's an old one, not the most modern. Let's see. And you know, maybe the configuration space looks like SE3, and if you study the topology of the space of rotations, you get this, which is real projective space of 3 dimensions. You can see that by doing quaternion parameterizations of SO3, the group of rotations. You can look that up in chapter 4 of my book if you like to go through the details. But basically you have 3 dimensions, right? You have X, Y, and Z, so 3 translations. And if you have a UAV, you can go, let's see, you can turn like this, right? I think that's called, oh, what is that one called? Let's see, that's roll. Roll. And you can have yaw, which is like this. And then you have pitch, which is like raising up or down, right? So you have 3 degrees of freedom for rotation, so that gives you 6. So instantly, if you have a rigid body, if it has all degrees of freedom, you have 6. If you have a robot, then for every one of the joints that can turn, you have another degree of freedom. Unless it has a shoulder joint or spherical joint, then you may get 2 or 3 more degrees of freedom. So you just take a Cartesian product of all of those. It could be R or S1, depending on whether the joint goes all the way around or whether it gets stuck. Maybe we have humanoid robots. I just saw an Iranian humanoid robot this morning at the University of Tehran, so I would have put the picture there, but I only had a few minutes, so that would be fun. So it may have dozens of dimensions. It could have 80 degrees of freedom. So then, if you want to plan for that directly, you're in an 80-dimensional configuration space. I've seen a paper by Alex Skolnick and Drake at MIT where they consider planning for 1,000 dimensions. So quite, you can get quite high on these. If you have multiple robots, then what you do is you take the Cartesian product of each one of their configuration spaces. Unless they are attached together, then they make what looks like the manipulator example or the humanoid example. But if they are apart, then you just have a configuration space for each one of them, and then you accumulate their dimension, right? So if I have 200 robots, then I guess I would have a 600-dimensional configuration. All right. So this is the method, the original one I just talked about, Lozano Perez came up with. If I have a robot that translates and there's an obstacle here, you can look at the set of all translations for that robot, no rotations. And you can easily slide around and make this really pretty picture here. I guess I should say Minkowski sum, right? So you know how to do these things. Very nice. But what happens now? Oh, yeah, that's very nice. That encourages us to think in the configuration space. So I'm very heavily biased by that too. I like the idea of finding the right space and solving the problem in it. Prior to reasoning in terms of the configuration space, and the whole problem is I want to get from here to here, I want to find a path automatically. There are some bad places that I need to avoid. They cause collision. That's what I want to do. And I think people made a lot of progress on motion planning after they identified the configuration space as the right way to look at it. Just like in physics, there was a lot of progress after Lagrangian mechanics was developed, because that's where the configuration space idea came from. And so it made its way finally into motion planning in the late 70s with Lozano Perez. And that's how we view everything. However, we get into trouble because if I want to represent this region here where the obstacles are, well, it was easy for this case, nice Minkowski sum. If you now allow rotation, you have a bunch of constraints like this. So even if I have a robot, let's say the robot here can rotate or translate and have an obstacle here, let's think about what kind of surfaces I get for the boundary of this. I want to represent that somehow. Well, if I bring this really close here, I can slide it up and down, or I can wiggle it back and forth, right? So that's a 2-dimensional surface. You can look at these very simple conditions and write it with taking an inner product of 2 vectors to enforce that condition. And then if you parameterize your rotations with complex numbers instead of sine and cosine like we normally do, then you can represent the surface you get from this contacting that, you can represent it with polynomials. So you get an algebraic representation of just that one case. But guess what? It's only piecewise algebraic because there's other cases, right? I have to look at every case where every edge of that robot touches every vertex of the obstacle. And I have to look at the cases of every vertex of the robot touches every edge of the obstacle. Because this thing can rotate, and you have to look at all combinations. Right? So that's quite a bit. There's a quadratic number of combinations. And each one of them produces some algebraic constraints. These are implicit polynomials. So before too long, when you go down this path, and let's say we can get even crazier, we can look at the 3-dimensional version of this, where we have vertices touching faces and edges touching edges. This will make very high-dimensional surfaces, right? I think I get 5-dimensional surfaces here that are the boundary of the configuration space. for this boundary of the configuration space obstacle. So that gets pretty bad. And, well, the number of pieces that you get is just crazy. If I define a robot using a CAD tool, maybe the robot might have 5,000 faces. And then the obstacles maybe will be another 50,000 faces. So am I going to take all combinations of that just to build these algebraic representations? And then when I do that, I have to deal with the fact that they are implicit polynomials. So that means that people have to do computations from, you ever hear of a field called computational real algebraic geometry? That's long. Let me write that down. So that's the field you need to get into then, to even handle these things. It's computational real, because there's a complex version, but you only need the real one. Because these live in the real world, so to speak. There's my whoops, real world, so to speak. Computational real algebraic, that means polynomials, in this case geometry. So it's reasoning about equations that are polynomials in multiple variables and studying the zeros of those. Right? It's called algebraic varieties, if you've seen that area of mathematics. So that's quite an interesting subject. There's a lot of work on that. And that's what you have to get into. It's not very easy. It has numerical problems. All sorts of crazy things happen. So quite a difficult and interesting subject. Now let's go back. Let's suppose I'm in a very simple two-dimensional space. If it's a two-dimensional space, I can do this kind of triangulation. I can do this kind of triangulation, which is not the kind I showed you before with sensors. This is the kind you know from computational geometry. I can just take my space, decompose into triangles, and then look at the dual graph, which I wrote in red here. And then if I want to get to any place to any other place, I just look at what triangle the robot is in, go to the centroid, and then continue connecting here, right? Just follow the path to whatever triangle I need to get to, and I'm done. People make cell decompositions like this, so that inside of each cell, it's very simple to do planning. What's the easiest kind of cell shape I can make? Convex, right? Because then, by definition of convex, for any pair of points, I can go straight between them without hitting an obstacle. So there's a convex decomposition. You can use whatever you want. If you want, you can get really crazy and implement Chazel's linear time triangulation algorithm, which I'm sure no one has ever done before. But you probably use the one that runs in time n log n from the nice computational geometry book written by those fine Dutch guys, right? All right. Let's see. Here, you can instead break it into trapezoids. You can do a planar sweeping algorithm. Computational geometers like sweeping. You can sweep across, and every time you hit a critical event, which is a vertex in this case, you draw a line above and below vertically. That makes trapezoids, including degenerate trapezoids, which are triangles. And then you just connect again the same way, same idea. So cell decompositions became popular in 2 dimensions. You can generalize that to 3 dimensions, n dimensions, but the problem that we get in motion planning is that if this would correspond to 3D translation only, once you have rotation, you're back into this algebraic geometry nonsense because it's very difficult because of polynomials. It's not linear. That's the big problem. Rotations are nonlinear transformations, and that causes a lot of trouble for us. Well, there are general methods. Going back to Schwartz and Scherrer, this was a method they developed based on something called Collins decomposition, which was a method that came from something called the first order theory of the reals. Have you heard of that? So it was basically if I make logic expressions using first order logic that also involve real numbers and polynomials, people wanted to know, can you determine whether or not those formulas are satisfied or satisfiable? Does there exist a point in Rn that satisfies them? Well, in order to solve that, they broke Rn into cells, and then they evaluated the signs of the polynomials at each one of the cells. So Schwartz and Scherrer realized, well, you can solve motion planning that way. You just do this thing called cylindrical algebraic decomposition. I could not draw a 27-dimensional example, but it works in any dimension. You just keep projecting and projecting and projecting dimension by dimension till you go all the way down to 1 dimension. Then you lift back up and you keep making columns of cells based on different kinds of events. One of them is this kind of event like this. There's another kind of event which is a crossover, which I didn't draw. It looks like this. So it's the same kind of idea. Just like the vertical decomposition that I showed you, this is like a vertical decomposition, but it's different in the sense that this one stops whenever you get here, right? The other one goes forever. So it makes a lot of cells. Turns out there's doubly exponentially many cells with regard to dimension, but it solves any path planning problem. So it's nice. At first, they showed that an algorithm exists that solves any problem. Then came Canny's roadmap algorithm, which was not doubly exponential, but was singly exponential. And that was so impressive that it made Canny won the Outstanding Dissertation Award from ACM, the Association of Computing Machinery, in 1987. So, quite impressive. It does some really interesting things. I don't have details to go through that, but it's based on some very interesting kind of sweeping that directly produces a one-dimensional structure, a roadmap, without having to project and project and project and then build all these cylindrical cells up. So it just immediately extracts out a roadmap. If you know Morse theory, it's very closely related to Morse theory. So there's certain kinds of sweepings that occur under that subject. It's a basic branch of topology. I'm not sure if it's ever been implemented. Right? So it's a beautiful algorithm, but again, you have to deal with kind of a heavy machinery here. It's still in algebraic geometry land. Also, you may or may not know this, but there's a lot of problems. There's also simple games on grids you can show. Very much like the two-dimensional motion planning problem we looked at on a grid, right, that Mansour presented a couple of days ago in the late afternoon. Imagine I want to rearrange a bunch of rectangles, and they only translate. That problem's piece-based hard. And there's grid-based versions that are also piece-based hard. So if you want general-purpose motion planning algorithms that can solve everything perfectly, I bet you're in trouble. Right? So that leads people to try to find simpler algorithms for particular problems. Here's motion planning for a labyrinth. Remember that problem I told you on the first day about trying to figure out all the pre-images for a line segment, right, or a simple beam that's in the environment? Well, this is the most closely related structure. It's called motion planning for a labyrinth. There's some very nice works on this. And you can very efficiently solve this problem and make a very nice cell decomposition. Here's what a projection of it looks like. They make these very nice cells based on analysis of all the critical cases. I think the question I asked about the pre-images is sort of like solving this problem, but then parameterizing the family of solutions with another parameter, which is the length of the ladder. Because those are the values that the sensor produces, right? So if you're interested in that problem, this is a problem to study in connection to that. So sometimes for a special problem, like planning for a line segment, there are beautiful algorithms. But if you try to do general purpose methods with these kind of combinatorial ideas, it seems it's impossible. It's very hard. That led people to develop sampling-based planning algorithms. So if we take a look at sampling-based planning algorithms, we input geometric models. We have collision detection algorithms. So that's kind of interesting. So a new black box has been made, let's say. Inside of this black box, you use the geometry that's been given. Maybe it's the CAD models again, computer-aided drafting tools were used to give all the models of the robot and the obstacles. And then the collision detection module will tell you whether or not a certain configuration is in collision. So that allows sampling-based planning. The sampling-based planning algorithm will ask the collision detection module, if I put the robot in this configuration, does it collide? And it may even answer the question for an open set around the configuration you ask, so that it's kind of protected, so that you can go step, 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 and try a chain of configurations and know that the whole chain is collision-free. Otherwise, you would need to ask an infinite number of times in the collision detection algorithm. And then we end up with methods that are not complete. Complete means it will find a solution if one exists. It will report failure if one does not exist. We instead accept something weaker, which is it will find a solution if one exists, but it may run forever if a solution does not exist. That might remind you from theory of computation of the difference between Turing decidability and Turing recognizability, where the Turing machine could be a decider that reports yes or no. That's like the complete algorithms. That's a high price you pay, it turns out, it looks like, and that leads to the piece-based hardness and that sort of thing. If you just want sampling-based algorithms, then you can get away with this kind of one-sided behavior, where if there exists a solution, it will find it. However, it's frustrating because if it does not find a solution, you are not sure if the algorithm is stupid, right? Or there just does not exist a solution. So it's a frustrating problem. There's probabilistic versions too, where you can say the probability that it finds a solution tends to 1. Long history of that. I'll just put some references there. Also, collision detection became quite a popular field. Particularly Ming Lin and Dinesh Minocha contributed a lot to that. Canny did at some point too with Ming Lin. And so you may have seen a lot of collision detection packages that are available from University of North Carolina, from Lin and Minocha. One big family is called Probabilistic Roadmaps, where they do it in the multiple query sense. In computational geometry, I assume you always think about this, right? Is it a multiple query problem or single query? If it's multiple query, then it may make sense to pre-compute some data structure, right? So what we do here is we pick a bunch of points at random in the configuration space, and then we try to connect them together to make a roadmap. Yes?
Are there any similarities between sampling-based equivalence and samples in particle filters?
They're both used, so between particle filters and sampling-based planning, they are both avoiding a very difficult computational problem by using sampling. And I would say those are also both related to Monte Carlo integration, which is much older, where people developed random sampling and quasi-random sampling, deterministic sampling, all sorts of sampling methods to evaluate integrals that are high-dimensional, right? In fact, those integrals show up in the particle filters. And I don't have integrals here. This is a different kind of problem. It's finding a path through a high-dimensional space. But yes, people have resorted to sampling in many different fields. And that's an idea that goes back at least 50 years. All right, let's see. So that's one family of methods. If you're in single query mode, then it's something that I call incremental sampling and searching. You may search the space a little bit, sample a little more, search a little more, sample a little more until you find a solution. You do not pre-compute a data structure. We introduced this thing called a rapidly exploring random tree. Many of you have heard of this. We introduced this in, well, the first paper at ICRO was in '99. We came up with the idea in '98. In fact, I was very interested in problems where there are differential constraints, which I'll say a little bit about in the end of this part. But if you have a control system, it is not necessarily trivial to find a path that connects 2 points together. So for example, if I want to get from here to here, and I have no obstacles, it's quite trivial, right, with a regular path planning problem. But if you have a control system, like you want to drive some kind of car and you want to get exactly there, and it's not trivial. It's called a 2-point boundary value problem. And so I was thinking about trying to make some kind of tree that can fill the space without having to connect to a particular point. So some kind of space-filling tree. That was the intuition I had. And so the idea here looks like this. It's been used in many, many settings. Like for example, if you look at the proceedings of the last ICRO conference, which was in Shanghai, that's just the main robotics conference, you can find the word RRT over 900 times. So people are using it a lot in robotics. The basic idea is I have this kind of tree where I pick a point at random. Let me draw over here and do that. So I'm growing some kind of tree. I'll describe it in kind of an inductive way. So in the space, I pick a point at random. I find the nearest point on the tree, say it's this, and then I try to extend toward the random point. In one version, I might go all the way there and put a vertex there. In another version, I might just stop early. So there's a step size. Usually you want the step size to go all the way, but there's some reasons for efficiency where you might not want to. And I can talk to you about that if you want. It's certainly mentioned in my book in detail, but there's 2 variations for that. I generally do not like parameters to tune. And there's no parameters in the sense that you need a metric for the metric space here to determine what nearest neighbors are. But other than that, you do not need anything else. But there is this epsilon if you want to improve the practical efficiency in some settings, which I can talk to you about if you're interested. So that's all the method is. Here's how it looks with a very small step size inside of a square. Here's how it looks if you connect all the way to the random point. And if you allow connections to interior edges as well, if that's the nearest point. So it very aggressively and very quickly explores the space in the beginning, and then gradually settles down to a uniform coverage. So it's very interesting. Asymptotically in the limit, it will be uniform. Even if this was not a rectangle, even if it's a very complicated non-convex space, I could start this in a simple polygon or in some very complicated high-dimensional structure that's non-convex, and it will still uniformly cover it in the limit. And these edges, if you look at it, are not very long. If you want to see some recent analysis of the properties, like the lengths of these edges, and ways to come up with more optimal solutions, you can look at this thing which I'm not presenting, but it's called RRT star. It was developed by Karaman and Frizzoli, who are at MIT, if you're interested. But basically the lengths are not very long, I'll say that. One way to understand this is in terms of Voronoi diagrams. So here's a Voronoi diagram put around the vertices. It's kind of hard to see. Here's how it looks up close. So, you know Voronoi diagrams, like where's the nearest subway station? So you divide a plane into regions. And if I do random sampling, some samples will fall inside of there, what I would call like the bounded Voronoi regions. Okay, these look unbounded, but I'm really exploring some bounded space. So I just mean that these are large Voronoi regions. So I have these interior ones and these kind of exterior ones. Right? Here's the exterior ones. So if I think about where the samples fall, sometimes they fall out here, and what that does is that expands the tree. Sometimes they fall in here, and that refines the tree. It's like a multi-resolution search. However, I do not need to implement Voronoi diagrams. I'm just explaining what happens. So it's a great benefit, because I think implementing Voronoi diagrams in some, I don't know, 27-dimensional configuration space with difficult topology and all sorts of things, weird metrics, I bet you don't want to do that, right? So this is having a bias towards that by very simple random sampling. So again, in my thinking, I was inspired by computational geometers, and I think there's this kind of thing I call Voronoi bias. If you want to solve a problem, you just generate a tree from the initial and a tree from the goal, and you spend some time trying to connect the trees to each other. There's different ways to do that. Basically, it's like a bidirectional search in basic artificial intelligence literature. You can find that. It's a very old idea going back probably to the 60s, 1970s, something like that. So that's how you solve a problem. One way, anyway, is to do a bidirectional search. The point is that I think a lot of earlier methods wanted to in a very greedy way, they make a potential function. Like, I need to get to the goal, so I should reduce the distance, but I'm not sure of the obstacles. And then you get stuck, and you have to wander around. Have you ever solved a problem where you have difficulty with local minima, right, and optimization? So that's right. So here, the idea is that do not try to be too greedy to go to the goal quickly, but spend a lot of time exploring the space in a very nice, aggressive way. And then only spend a little bit of time trying to connect together. So being too greedy helps you sometimes, but most of the time you can get in trouble. So this is a balance against the excessive greediness. Greediness is not very healthy anyway, right? So good for the algorithm. It doesn't always work too well. Maybe if with these two trees they cannot escape some little narrow passages, maybe you need to grow more trees. People do research on that. How many trees do you need? If you need to start new ones sometimes, and then connect them all together, things like that. That's the kind of issues people worry about in sampling-based motion planning. So they can't solve everything, but they do solve some good industrial-grade problems. These kind of methods, either RRTs or similar kinds of single query search methods, solve problems like this. This is from a company called Kineocam. It's started by Jean-Paul Ramon in a CNRS in Toulouse, a laboratory called LAS. And they have a model here. This is an application that's not directly robotics. Here's a geometric model of the hood of an automobile, and they want to figure out whether or not they can insert this motor, which is the motor for a windshield wiper. They just want to know, can I insert it and remove it without actually building it? Well, you can use motion planning for that, right? It's the same problem. So that's what they did. It's a company that makes motion planning software, and many companies use this to determine whether or not their designs are feasible. That's called virtual prototyping. Very big field. Another example is sealing cracks in cars at the Volvo plant in Sweden using manipulators. So motion planning algorithms are working successfully for that. There's been a lot of success in virtual worlds. So maybe I have a virtual human, a digital actor. I think Frank must have talked about virtual humans and digital actors. Has he talked about that at all here? Some of that, at least in the beginning. I know he talked a little bit about that. So, so maybe you want to do motion planning here. You ask this digital actor to, in this virtual world that you've created, to reach into this lower refrigerator and grab something. So all of the motions are planned automatically. These are some examples from James Kuffner at Carnegie Mellon, where you maybe have a whole field of actors and they're all running along, and you can use these kinds of planning algorithms for automatically generating their motions. Also, there's humanoid robotics where it's been applied, starting in Japan. So in this case, these RRTs, these rapidly exploding random trees, were used where you tell a humanoid to grab the flashlight, it figures out all of the motions by itself. And then it works on the real robot. So very nice. Also, there's been applications to computational biology. So it turns out that understanding the structure of molecules, I know that in Professor Mohades's group there's interest in computational biology as well. So the studying and sampling the conformation space of molecules for protein folding and drug design, turns out that the models for that are not too far off from robotics models of exploring configuration spaces. So these rapidly exploring random trees have been produced quite a bit. This is an old picture from Nick Simeon from the same group that Jean Baudemont was actually at that time. And other people like Juan Cortez and many others have applied RRTs for molecular biology problems. All right, now if we go beyond basic path planning, and this is what I thought when writing my book, we need to broaden the focus of planning and address these important concerns like feedback, differential constraints, sensing uncertainty, and where does information come from? Well, it comes from sensors, as I said. It's not written down nicely for us. So those applications I showed you, a lot of them are non-robotic because it has perfect information requirements. That's why it's been very useful for video games, automated movies, virtual prototyping, any kind of virtual world where you make a perfect model. Motion planning has been much more useful for, I would say, because the algorithms work very nicely for this. In sort of real hardcore robotics, you ultimately have to deal with feedback, differential constraints, and sensing. That's what motivated me to go further and further down the path of sensing, which led to this course. All right, so if I think about it, we'll take a break just a little bit, but when I think about it, I look at these different subjects: control theory, motion planning, as I've just given you an overview of, and artificial intelligence planning. Each of them has some different characteristics historically. I put some black circles for what these subjects dealt with historically, and what their main core focus was. Like, for example, control theory, continuous spaces, analytical in the sense that the solution is in the expression on the board. You know, it's a mathematical formula for the solution to solve a differential equation. They use differential equations, they care about optimality a lot, and they know feedback is essential for everything. Motion planning, however, continuous space, but very algorithmic instead, and they only care about feasibility for the most part, not optimality. And then AI planning starts off discrete, also algorithmic, also feasibility. However, in modern times, and I put these extra circles here, the white ones, for what I see people covering in modern times. Like, for example, control theorists are now very interested in continuous and discrete. It's called hybrid systems. And they're also interested in algorithms and feasibility and uncertainty, all sorts of things. So, so all of these subjects are kind of, let's say, colliding. You know, they're interested in the same kinds of things. So I could call it planning algorithms. I could call it algorithmic control theory. You could call it some kind of artificial intelligence if you want. It doesn't really matter. I think all of these encompass the kind of things we care about now. It's just that people come from different backgrounds and they look at it in different ways. I'm going to take a break right now for a few minutes, and then I'll do the next part.